Thanks to everyone for joining us here today. You're gonna hear a little bit about the hub's work in understanding this important phenomena that we refer to as carbon uptake. That is the permanent sequestration of CO2 into cement-based products over their life cycle and into end of life. Just to kind of kick us off and put us a little bit into context, is that all of us know that when we think about the environmental impact of a material, we have to take a life cycle perspective. It's important to understand and to reduce the emissions associated with producing those materials, but a material's impact goes far beyond that. We know that the impact of a material is driven by the emissions associated with turning that material into a building or a pavement or infrastructure or product. Materials can influence the energy use of buildings and vehicles during the use, and they can have impacts at end of life when a structure reaches its end of life. But what we're going to talk to you about today is our research and trying to understand and quantify, and even more excitingly, how to manage or increase this somewhat unique phenomena that goes on within cement-based products, which we refer to as carbon uptake. So with that, I'm going to turn it over to Pranav, and he's going to tell you a little bit more about what we've learned.
Thanks, Randy. Hello, everyone. Before I get into the weeds of the research project on the carbon uptake, let me quickly start by reminding ourselves about what exactly is carbon uptake. So as we all know that with concrete being the second largest consumed material, it has a wide range of applications spanning from pavements to bridges to buildings and several other infrastructure that we see in our daily lives. One of the interesting process that happens within concrete is that it naturally absorbs carbon dioxide from the atmosphere around it, and it permanently binds it within itself. And this process is known as concrete carbonation or carbon uptake, since it permanently sequesters CO2. So for example, let's consider a small cross-section of the concrete element as shown here. And since this is a cross-sectional view, this face here represents the outer surface of the element which is exposed to the atmosphere. And this element is not carbonated when it is just built. However, the carbon dioxide that's present in the surrounding atmosphere slowly diffuses into the concrete, and there is a chemical reaction that occurs by which the calcium hydroxide inside the concrete is converted into calcium carbonate, and thus the CO2 is permanently sequestered into the concrete element. However, this process occurs slowly over a period of time, which could take several years. And we can observe that the carbonation front or the depth of carbonation increases over time. While there are several factors ranging from material properties to environmental conditions to exposed geometrical surface of the concrete, which determines the extent to which the uptake has taken place, we can say that this natural mineralization of the atmospheric carbon dioxide, that is carbon uptake, by the concrete elements offers a great mechanism for neutralizing a portion of their life cycle greenhouse gas emissions. So for instance, let's take the US pavement network, which has the potential to absorb approximately 5.8 million tons of carbon dioxide by the year 2050. And as I mentioned previously, this depends on several parameters ranging from material to climate to application-related factors. Now, let me pause for a minute here and ask the audience as to what do you all think could approximately be the percentage of calcination emissions that could occur or can be sequestered in US single-family buildings? Any thoughts, guesses? So we can see that most of you have answered like it's approximately like 5 to 20% of the calcination emissions, followed by like about one third of the audience said it's between 20 to 40, and 20% of you said it's less than 5%. And I'll keep this in mind, and I will get back to this same question in some time later in the presentation and show you what some of our observations are for the single family houses. Anyways, the bottom line here is that natural carbon uptake is an engineered solution for reducing and neutralizing the concrete and cement industry's greenhouse gas emissions. And various stakeholders ranging from architects to designers, cement concrete producers, LCA practitioners, PCR developers, and policymakers across the value chain can leverage uptake to reach carbon neutrality goals. So recently, we have seen how carbon uptake in concrete construction is gaining momentum, and IPCC in their sixth assessment report mentioned that the natural carbon uptake in concrete is an important carbon sink measure. And currently, there are several reports and standards that are available which provide guidelines as to how we can estimate carbon uptake of cement-based products. For example, the IVL report that's published by the Swedish Environmental Research Institute that provides 3 different calculation methods to compute the use phase carbon uptake. The first one being the tier 1, where it's a simplified calculation method that requires minimum amount of data, such as the time of carbonation, the amount of concrete, and cement clinker. But this computation is considered to be is considered to have a very high uncertainty associated with it due to the lack of other environmental and application-based information. At tier 2, we have an onward calculation method, which is modified to include common application types such as bridges, pavements, or buildings that cover approximately 65% of the cement consumption. And there is uncertainty associated with this as well as to how the application-based information is modeled and integrated within the uptake calculation. At tier 3, we have an advanced calculation method, which recommends the use of a software model that includes various different details to compute carbon uptake at a national scale. However, the modeling framework here is complicated, and the complexity primarily arises with how the different providers define the various aspects listed in the tier 3 calculation as highlighted in the image here. Then we also have a standard, the EN 16757, that is widely used across different regions for calculating carbon uptake. Once again, the approach that's delineated in this standard is simplified and easy to use. However, it is a generalized methodology that follows a deterministic approach and do not account for data variability. And at present, there is no method to systematically calculate regional context-specific carbon uptake that can incorporate user-level and application-based input information. And therefore, we see that it is important to incorporate the variability associated with the input information as part of the carbon uptake estimation process, since the carbon uptake values are sensitive to changes in environmental conditions, as well as application-based factors such as geometry and the type of material being used. Therefore, the questions that arise here are, how can we actually account for the uncertainty due to the assumptions and the lack of sufficient information? How can we systematically define the different end-use levels to reduce the uncertainty? And finally, how can we incorporate region-specific data and the associated variability? So at CSHub, the aim here is to develop a context-specific carbon uptake model that incorporates a probabilistic framework to capture the uncertainty. And to build this model, it is important to collect region-specific and context-specific data and develop an input database integrating all the available information. And finally, it is vital to report the carbon uptake to effectively communicate the results with the different stakeholders. So to develop the context-specific carbon uptake model, it is important to understand the interaction and influence of the different input factors. Therefore, we start by defining our big boundary condition, which is the region that we are considering. And then we define the context, which could be the application and the associated components. So at the highest level, we have sectors such as housing or other infrastructure elements into which concrete goes. Followed by, we have the different archetypes such as single family housing or office buildings, pavements, etc., which is followed by different elements like slabs or concrete walls. And finally, we have products such as CMU units or precast panels. The idea here is to compute the carbon uptake at the bottommost level and integrate the results for a given application. So as we go down this route, they define the different components that comprise the big sector or the bigger element. Whereas as we go up from down here, it defines a complete application. So the factors affecting the carbon uptake can broadly be divided into three categories: material, location or environmental factors, and geometric factors. And this breakdown in application is significant for carbon uptake calculation because the type of application or the component influences the geometric factors as well as the cement or the concrete material properties. And the maximum carbon uptake that is possible is dependent on the material type, while the carbonation characteristics are such as the rate of carbonation or the degree of carbonation are influenced by both the material as well as the location-specific climate factors, such as carbon dioxide concentration, temperature, and relative humidity. The next step here is to collect sufficient information since the efficacy of the model depends on the quantity and the quality of the input data. Therefore, we start by selecting a region of interest and collect the different end-use stock that includes different types of buildings, pavements, and other infrastructure. Then build different archetypes for each end-use stock. So for example, if it's buildings, we could divide it into commercial buildings, residential, or warehouse. And once we build the different archetypes, we identify some of the key attributes that influence carbon uptake for, let's say for buildings, it could be some of the geometric parameters like the building height or the building footprint, which is the floor space, foundation type. And in addition to these, some of the local climate factors, exposure conditions, the mix design, etc. And once we identify the attributes, then we explore available databases, standards, different records and reports to collect information regarding these attributes. And this would help us to develop an integrated database with range of different input information that we can use for our analysis, and then we can extend the same methodology to other contexts and other regions as well. So to begin with, let me consider an example here to understand how this methodology is used to calculate the carbon uptake. So as you can see here, the calculation setup uses the information from the database that we develop. And an important point to note here is that this is calculating only the use phase carbon uptake calculation. So the example here that I'm showing on the right side here is for a particular concrete component, which is a concrete grade slab of a single family house with 1 story and the floor area being around 2,500 square feet. The slab being 4 inches thick with a compressive strength of 3,000 PSI and a cement content of 230 kg per meter cube. As shown on the right side of the slide here, the yellow cells represent cells where the input information or the information is manually input, and the orange cells here have predetermined list of input information that we collected for our database development. And the carbon uptake results are reported in 3 different ways: as absolute carbon uptake value, or as uptake fraction, also as uptake per unit volume. And suppose some of the information that's shown here is unavailable to the user, the model will select a range of values for the input parameter that does not have input from the database that we are developing, and provide a distribution of carbon uptake values. But we can see how rich the input information should be for us to calculate the carbon uptake. And therefore, in order to perform this, it is important that we define the different input levels as well as the different components associated with each level. So for example, if we take a building application, at the application or asset level, which is the topmost level, we can classify it as different residential and non-residential buildings, such as single family, multifamily, or office buildings. At the second stage, which is the element level, we can find the different concrete elements, such as floor slabs, walls, foundations, columns, etc. And the next level would include the different exposure conditions like the outdoor, indoor, and other exposure conditions. And finally, we have the geometric level with the different dimensions being defined. And therefore, as we move up the ladder here, due to decreased granularity of information, there is a high uncertainty with the results that we get. So let me now take an example where we consider a single family house with the highlighted component. So it's the concrete goes primarily into floor slabs, walls, and foundations, and we consider the different combinations of environmental and geometric factors. So let me go back to the same example that I showed a couple of slides back with where I have all the details in here. So this is the most detailed level where we have even the geometric properties input into the model. And since we have all the input information here, we get an accurate uptake value of about 31.96 kilograms CO2 per meter cube. And here I'm presenting the results per unit volume so that it is easy for us to compute the absolute carbon uptake value or the uptake fraction based on the volume and the emission information that's available. So although we have an accurate value here, one of the underlying assumptions in this analysis here is that the length and the width of the concrete slab that I considered here is kept the same. And that's just to minimize the amount of calculation complexity. But in practice, we can say that this could go either ways. Like one of the dimension could be greater than the other dimension. And once we incorporate this variation, it gives us a distribution which looks quite accurate because I'm considering a wide range of carbon uptake values. But if we take a closer look at this, we can see that a small variation due to the change in the aspect ratio that I showed here causes a small range of carbon uptake values that's possible for even at the detail level. And this would give us like an average value of about 32.04 with a standard deviation of 0.05. In fact, the lower end of the distribution here represents a square shape. And as we increase one dimension over the other, the uptake value also increases. And this kind of shows how architects or designers could play an important role in optimizing the geometrical design of these components. However, now the challenge arises when we do not have an accurate value for the geometry. And the question is, what do we do next? So in order to address this issue, we go back to exploring the different context-specific data sources. For example, in the context that we are considering here, which is a single-family housing, we collected some information from different specifications, such as the International Residential Code and the ACI 332 code requirements for residential concrete, from which we can collect some component level geometric range of values for the different geometric components. And in addition to these code specifications, we also looked into American Housing Survey database that provides us with the distribution of some of the salient features associated with single-family houses. So an important step here is to also identify the different context-specific concrete elements for the single family houses that we are considering. So based on the specifications that we looked into, the ACI 332 and the IRC 2024 documents, we can classify the concrete elements broadly into three categories: foundation, floor slab, and walls. And the American Housing Survey is used to identify the different types of foundation. So as you can see the chart here in the top left corner, we have three broad foundation types being defined, one being the concrete slab, followed by crawl space and basements. And for the floor slabs and walls are primarily above grade solid concrete elements. And using IRC 2024, we further broke down the foundation types into different concrete elements. For example, for the concrete slab, we can say that the concrete goes into grade slab and footing element. For the crawl space, it's primarily the footing into which the concrete goes into. And for the basements, it could be grade slab, footing, and the basement walls. And in addition to these, we should also consider the above grade elements like the floor slab and walls. And for the above grade elements, it could be made out of concrete, or it could be a non-concrete material such as wood. And this is a crucial step for us to ensure that we are able to analyze these scenarios, the different scenarios with different combination of concrete elements to understand how carbon uptake values vary and the different input parameters that impact the carbon uptake calculation. So with that in mind, let me show you a quick example of a single family house. Let's say it's made with wooden walls. And we can consider that concrete primarily goes into the slab element and basement structure, which is footing and basement wall. So in the first scenario here, let's consider this structure having wooden above grade wooden floors, and performing a Monte Carlo simulation using the range of different input parameters, which I will show in a minute, that we have collected from the data sources that I mentioned. We can see that the carbon uptake value varies from 19 to 30 kg CO2 per meter cube, with an average value of about 24.9 and a standard deviation of 2.2. This kind of translates to approximately 24% of calcination emissions. And suppose we change the above grade floors to concrete floors instead of wooden floors. We observe that the carbon uptake values now vary from 27 to about 40 kg CO2 per meter cube, with an average of about 36.6 and a standard deviation of 3.3, which translates to about 35% calcination emissions. So going back to the question that I had asked at the beginning as to what could approximately be the amount of calcination emissions that can be sequestered in a single family housing, we can see from this example here for the single family housing that it has a potential to absorb approximately 20 to 40% of the calcination emissions over its entire life cycle or the use phase stage. And once again, I want to remind everyone that this depends upon the input factors that we consider. So there are several input factors like the geometric specifications or the material specifications and environmental conditions. So here we have varied only the geometric application-based or the context-specific geometric values. So when we conduct a sensitivity study to understand or identify what are the major contributors that impact the carbon uptake distribution. For the first case, for the wooden floor case here, we can see that the major contributor to this spread of carbon uptake values is due to the basement wall thickness, followed by the grade slab thickness, and then we have a number of stories. The red or the negative direction here implies that increasing these values, these individual parameters from their minimum specified values in the codes to the maximum range of their specific values decreases the carbon uptake potential. Only the floor slab factor is observed to increase the carbon uptake as the area increases, but that's quite negligible in this case because it just contributes to 1% of the carbon uptake variation. So just to understand what this sensitivity plot means, we start our analysis by choosing the minimum values for all these 9 input factors that's shown here. And we try and change the input factors ranging from the minimum to their maximum values. And this uptake range that we obtain here is primarily due to the effect of basement wall thickness range. So 86% of this variation is observed due to the basement wall thickness. So before I present the, let me go back to. So before I present the major contributors for the concrete floor case, let me put this question out to the audience as to what do you think could be the most influencing factor for the concrete floor case where the above grade slabs are made out of concrete material? Any thoughts, guesses? So we can see that most of you, about 50% of you said that it's the floor area, and about 20% of you said it's the number of stories, followed and basement wall thickness, and also the grade slab thickness. And let me present my results. I would say all of you are correct, but for this case here, we can observe that it's the number of stories that's the major contributor here, primarily due to the change in the exposed surface area of the floor slabs for any given floor area, followed by the basement wall thickness and floor area. So it's great that all of you could kind of guess how the variation would occur. And once again, we can observe here the trade-off between the two cases that I show here is that the number of stories and the floor area here contributes in, as we increase these two parameters, the carbon uptake value increases. And as we increase the other factors, it kind of decreases. But what's crucial here, or the bottom line here, is that the component thickness, number of stories, and floor area are 3 major factors that play an important role in the uptake calculation in this context. And it is important to have an accurate information about these factors in order to reduce our uncertainty. So for example, in the first case here, if you have the basement wall thickness, then it helps us in cutting down the range of values to maybe a minimum small range of carbon uptake values. And so moving on, in the previous slides, we saw how we can compute the context-specific carbon uptake and report the results as an absolute uptake value or as a fraction or as uptake per unit volume. Another method could be to use EPDs or environmental product declarations of cement-based products as a resource to report the carbon uptake values. And over the past few years, we have seen that EPDs have provided a standardized framework for conducting life cycle assessment of cement-based products, and there is a need in the industry to include the entire building life cycle into EPDs. And in this sense, including carbon uptake in the EPDs will provide a more comprehensive understanding of the environmental performance of the cement-based products. And it will also aid the stakeholders in comparing different products, designs, and also to make an informed decision when choosing materials and other design strategies. But the question here is, how can we how can the carbon uptake of different end use applications be standardized through EPDs? So often the producers who prepare the EPDs for their mixed designs may have material level information such as the cement type, the binder content, and the strength of the concrete, but nothing related to the end use application of the concrete or the mixed design that they're preparing. And from a carbon uptake perspective, this results in a significant amount of uncertainty due to the vast applications into which the that particular mixed design could go into. And reporting a conservative uptake value from just the material level information could be unrealistic in nature. But we know that the downstream user may know some or most of the information related to the application, geometry, and location. And our goal here is to ensure that EPDs can help in this transfer of information, and the users can leverage the end use information that's available to them. So typically, as I mentioned, like the producers develop the EPD based on the information at the material level, but we can define different levels based on the granularity of information that's available to the user. So at the highest level of application-based levels, we have the application type followed by the different concrete elements, the exposure conditions, and geometric information. With the help of this model and the database that I showed previously, we can eliminate the material level altogether and have the levels begin from the user phase. So at the level 1 here, we can get multiple different distributions representing different applications such as buildings, pavements, and other infrastructure, and use these distributions to come up with individual values that could be reported in the EPDs in the form of charts or tables for each mixed design. And further moving down, we could obtain distributions of carbon uptake at each level for the different components associated at those refined level. And this would help us in cutting down the uncertainty associated with the carbon uptake results, similar to the plots that I showed for the single family houses previously. And in this way, we can see how we are able to kind of remove the uncertainty associated at the production level and make it simpler and less conservative for the users. So at CSHub, we have published a report with a working group to describe this methodology to account for carbon uptake in North American product category rules for EPDs of cement-based products. And it is publicly available on our website. So if you're interested, please go ahead and scan the QR code shown there to access our report. The main aim here is to provide consistent guidelines for the EPD development process such that there is a flexibility for input variables at different levels. And the goal of this consistent methodology would be to ensure that it's used over a wide range of climatically diverse regions as well as applications. And additionally, the data that's generated and organized as part of this effort will benefit both the producers as well as the users to get a better understanding of the carbon uptake. And the stakeholders may find it easier to make sustainable choices once we have this reported. So some of the key takeaways from today's presentation are that a probabilistic context-specific model helps in systematically computing the carbon uptake values, as well as in capturing the uncertainty associated with it. The information from the regional databases, the different reports and standards that we have collected help in improving the quality of the input information for both historic and future context-specific carbon uptake calculations, as well as it helps in communicating the results with architects and engineers and other stakeholders. And the model enables the building stakeholders with a user-friendly model that could calculate the carbon uptake and embed this in the building lifecycle assessment. And context-specific carbon uptake and the subsequent reporting of this in EPDs can help the stakeholders to use EPDs to calculate the carbon uptake based on user-level information that's available to them. And for the example that we considered here, a single family house, we observed that the thickness of the different components, the number of stories, and the floor area are major contributors that help in reducing the uncertainty associated with the carbon uptake calculations. And moving forward, our aim here is to build a national level inventory for selected regions with input information regarding the typical archetype geometry, as well as exposure characteristics. Then to develop a dynamic carbon uptake model to incorporate the interaction between the environment and carbonation, and finally implement the model to determine future trends and forecast regional level of carbon uptake projections. And that in mind, over to you, Randy.
Yeah, thanks, Pranav. If you could go ahead and animate that up, that'd be great. So one of the things I just wanted to end on a thought here, which is that as Pranav showed, there's been a lot of research to understand, to get as best possible estimate of what the magnitude of carbon uptake is in cement-based products. But I think along the way, one of the things we came to realize that's particularly exciting is there's a lot of opportunity to maximize the amount of this uptake, right? We can think about, as Pranav was just alluding to, architects have the opportunity to think about the geometry of the structures. The structural designers can take into consideration and make sure that we're not specifying stronger mixes than are needed, because the stronger that a mix is, the slower the uptake occurs. So there's another opportunity there. We can make sure that when we deliver those mixes, that the concrete producer is working with their supply chain, their testing supply chain, et cetera, to make sure that we're not having to over design those mixes for strength and therefore maximizing that uptake. And then finally, there's sort of a set of stakeholders that are, whether we're talking about owners or policymakers, those that are engaged in LCA and EPD development, is to make sure that these kind of assessments are included so that we are incentivizing stakeholders to maximize that kind of uptake. And uptake is just obviously one of many strategies for managing the carbon footprint of the built environment. Obviously we need to be making sure we're putting the right material in the right application, that we are using that material efficiently, that we're accounting for the benefits of particular materials, whether they improve energy efficiency, improve durability, improve fuel use, whatever those might be. But this is just another sort of arrow in the quiver, if you will, of strategies to make sure that overall that we're minimizing that impact. So we want to thank everyone again for joining us. Hopefully we can get some more questions here popping up into the Q&A. I think, Andrew, we had one question that had already come through, which is sort of related to the topic that I was just talking about, which is that when we produce cement-based concrete, just like when we produce any material, there are emissions associated with it. And so how do we, should we be using that material? Should we be counting on uptake? There's a couple of things that I would point out. So what I was just saying just a moment ago is true. If we were, some of our most powerful strategies for managing the greenhouse gas emissions associated with construction are material efficiency. We've had some recent studies within the hub coming out of Caitlin Mueller's digital structures lab that's shown that we could build structures that are as durable as current concrete structures with less than half and sometimes up to 3/4 less material than we use today. Part of the reason I point to that is in any of those cases, the designs that have come out of that work, not only do they use less material, but they actually have more surface area than any of the designs that Pranav was just looking at. So it's actually would not only reduce the upfront burden to be very carbon competitive with any other strategy just right out of the gate, but we would fairly rapidly have a significant amount of uptake associated with those structures. Another powerful lever is to shift away from clinker-based cements into blended cements, supplementary cementitious materials. Many of those materials also have uptake potential. And so, again, reducing upfront burden while still gaining some of the gaining benefits of this permanent sequestration out over time. And then finally, I do want to address what is sometimes a misconception about carbon uptake. It happens most rapidly at the beginning of the life cycle. And so while it's true that it may continue on for decades out into the future, there is a significant amount of that uptake that occurs early on. And we've actually looked at in for some cement-based products, the gains that Pranav was alluding to there, the up to 40% of reabsorption of calcination emissions can in fact happen within the first decade of the life cycle of that structure. So this notion that these kind of benefits only accrue out into the far future is a misunderstanding of the way that carbon uptake occurs, at least in some cement-based products. Looks like we have a couple other questions. So Pranav, you might be able to take this one. So will uptake be considerably higher for infrastructure where you almost always have exposed concrete? So you have pavements, bridges, retaining walls. I think the notion being that, in those structures, we're always almost looking at the concrete. It's just on the surface, as opposed to
Yeah, absolutely.
in a
Absolutely.
building where you might have carpet or you might have paint.
Absolutely. Yeah, yeah. That's a great question. Like, as I mentioned in one of the initial slides, that the exposed surface area is kind of important for the calculation of the carbon uptake. And with the other infrastructure elements having concrete, like concrete pavements or bridges, having most of it being exposed to the atmospheric carbon dioxide, it is going to have like more carbon uptake. But another factor here that we should consider is if they are being, if there are any coating materials being applied on these infrastructure elements. So if we have, depending upon, having different coating materials like sealers or acrylic paints that's applied on, let's say, bridge piers or bridge girders, we could have that negatively impact the carbon uptake values. So that's an additional point that could impact the adverse effect on carbon uptake. But otherwise, yeah, the exposure
Yeah.
is
I
the
think
most.
one of the things that we've seen with a lot of the infrastructure type applications, and I think pavements being and retaining walls kind of being some of the more probably the most extreme example, is that while it's true that one surface is completely exposed, often the other surface is, literally buried, and as a consequence can have a fairly slow uptake. Whereas the architectural structures that you were showing, the columns, the beams, they are they often have multiple, if not four, surfaces that are in some way or another exposed. And Pranav, you just alluded to another topic that I think often has misunderstanding associated with it, in that you pointed out that coatings can, you said, adversely affect. They can slow down the uptake process, but they don't actually stop the uptake process, which I think is something that's often an assumption, that, or at least that I've run into before. Maybe you could just comment on that just a little bit.
Absolutely, absolutely. I think that's one of the key points of carbon uptake as part of the life cycle LCA analysis for concrete elements, because it's a natural process. It is going to happen one way or the other over a period of time. So even if you have like a different coating surfaces or a cover on concrete elements, there is some way by which the carbon dioxide could diffuse into the concrete elements. The only thing that it does is it slows down the process. So over time, the amount of carbon uptake that's happening within the concrete element would decrease. But yes, there will be some amount of carbonation that occurs over the entire life cycle of
Yeah.
the
And so
element.
that's actually a good setup for the third question that we received here, which is that, even if that might slow it down over during the use phase, there's also the end of service life that's associated with any of these products. And so the question was basically, do we have CO2 uptake at end of service life? Are there ideas on how significant that is and how we might manage or maximize that?
Yeah, that's a good question here. And yeah, as I mentioned previously, like for this presentation, we have shown only the use phase carbon uptake for the buildings example that I showed. And the end of life carbon uptake also plays a major role in the total carbon uptake value that's possible for the concrete elements. And this once again depends on the context, and that's why we are focusing on different contexts to be mentioned because, for example, if it's a building, we have observed that roughly about 15 to 20% of the entire or the maximum potential carbon uptake occurs during the use phase, and the rest is open for the end of life carbon uptake. Whereas for pavements, it's observed like close to 50% is achieved at the use phase, and the rest 50% is the potential for end of life. But how much of this remainder of the 80% or the 50% of the carbonation is possible, once again, depends on different end of life scenarios or different factors that affect the end of life calculation, such as the uh, the period of stockpiling or the period of time when the demolished concrete aggregates are exposed to a particular condition. Also, the height of the different stockpiles play a big role. The different grain sizes into which these concrete elements are demolished and stockpiled also play an important role in calculating the total end of life uptake that's possible. So there are several factors that influence the end of life carbon uptake, but uh, definitely there is more potential at an end of life carbon uptake stage.
Yeah, and just to make sure that everybody's follows the idea there is that um, in ultimately what determines the rate of this process is the amount of surface area that's available, right? There's many other fine details there in terms of humidity and the mix chemistry, et cetera. But one of the key determinants, the surface area, and at end of service life for concrete, we crush it up and create many-fold the amount of surface area that was available during end of life. So that's why it's a really actually potentially really exciting source of uptake as well. We have a question here about how can we balance between I guess, the benefits of natural carbon storage through carbonation and the concerns about steel reinforcement corrosion that can be associated with carbonation. Do you have any thoughts on that,
That's a good
Pranav?
question. So one of the aspect that is to be understood here is that the carbonation, as we mentioned, it's a very slow process, and often the structural designers provide sufficient amount of concrete cover before when they design the concrete elements. And more often than not, we have like at least 2 inches of cover for the reinforcement, and we observe that even over the entire life cycle of these elements, we don't really reach up to a 2 inch cover for these elements. But this once again depends upon the exposure conditions as well as the exposed surface area. So for example, if a slab which has a very high exposed surface area and it is exposed to very severe conditions, then we would have the carbonation front moving faster. But in most cases, the engineers would consider this factor and provide sufficient amount of cover, which will help in kind of cutting down or not having that negative impact of carbon corrosion of the reinforcement due to the carbonation process.
Yeah,
So
I think one way to maybe to sort of say that is in an application where that is, where you have steel reinforcement that needs to be relatively near to the surface, then you should choose a mix and a design such that that won't become an issue, right? Like, because in the end, the durability of the structure is really important for its sustainability. But having said that, there are many, many applications where that steel reinforcement is either not present because of the application or is sufficiently deep. And in those cases, we should maximize this I think it's just basic. We're not ever suggesting to not take that into account, but in opportune cases where it's possible, we should do what we can to maximize this carbon storage. And then finally, we had a question sort of coming back to the alternative sealers or to coatings, and sort of putting out there the idea that maybe we could add into silica or silicates as an alternative to sealers. And so I don't know if you had any thoughts on that one. We might have to defer that question to our colleague that's not here today, but it's a really interesting one that we should explore. I think to me, the flip side of that is whether or not that interferes with the ability, like the silicates are not the constituents that are recarbonating. So I'm not sure what that trade-off might turn out to be, but it's certainly one that we will look into. So appreciate that comment.